Hello everybody. In this video we're going to continue the introduction to the chemical reactions that we want to cover before discussing the mass balance for reactive systems. In the previous video we discussed the stoichiometry of the reaction and how it's important and how we can use it to calculate or find out how much of the reactants and products are being used and produced given one quantity or quantity of one of the reactants or one of the products. Now we are going to discuss a very related thing, which is what we call the limiting and excess reactants. And to understand this, let's look at this example that we have here. We have sulfur dioxide reacting with oxygen, producing sulfur trioxide. Before anything, we need to make sure that this reaction is balanced. So we have two atoms of sulfur here. We have in the product two atoms, so it's the same. We have four oxygens and two more, so this is 6, and we have 6 atoms of oxygen in the product. So the reaction is a balanced reaction, so we can proceed. The reaction is telling us, or it's showing that 2 moles or molecules of sulfur dioxide, 2 moles of sulfur dioxide react with 1 mole of oxygen, producing 2 moles of SO3. And we are going to discuss 2 cases, and these 2 cases are the first is feeding 20 gram moles of sulfur dioxide and 10 gram moles of oxygen to the reaction. And assuming that the reaction will go to completion until all the reactants are consumed, then we will have 0 gram moles of SO2 and 0 gram moles of oxygen, and we will have 20 gram moles of SO3. And this is because the sulfur dioxide and oxygen are fed with the same stoichiometric ratio. So it's 2 to 1 here, and this is 2 to 1 here as well. So in this case we have only SO3 in the product, meaning that if we put the 20 gram moles of SO2 and 10 gram moles of oxygen in a container, let's say a beaker, and we closed it and we let them react until all of the reactants are consumed, we will end up with a beaker filled only with 20 gram moles of SO3. So it started with 30 gram moles and it ended up with 20 gram moles. So this is one case, and in this case, as we said, they are fed in stoichiometric proportions, and no reactants will be present if reaction proceeds to completion. So this is the first case. The second case is the same reaction, but with different feed flow rates or amounts. And there is a point that must be clear here, that there is a big difference between the amounts that are fed to the reaction and the amounts that are reacted or that are reacting. So just to clarify this, when we look at the ratios, it's 2 to 1. It doesn't necessarily mean that what I'm going to feed to the reaction is with the ratio of 2 to 1. So this is what we have here is kind of it's not a special case, but it's not a general case. The general case is something like this, that we feed the reactants, and one of them or the ratio between the reactants is not the same as the ratio between the stoichiometric coefficients. And for example, let's say I have 20 gram moles of SO2 and 500 gram moles of oxygen. It doesn't mean that the 500 gram moles are going to be all consumed. It's just more than what I need, and it doesn't mean that the reaction is not going to happen. It's going to happen, but what the stoichiometric ratios are dictating is how much oxygen is reacting with SO2. So even if I have the 500 gram moles of oxygen, it's not all the 500 gram moles will be consumed. Only according to the ratio or the stoichiometric ratios, the amounts would be calculated or will be consumed. So this is a very, very important point, that I have the freedom to feed the reactants with any ratio. I don't have to be limited to the stoichiometric ratios. I can add any amounts, but the amounts that are going to react will react according to the ratios here. So I hope this point is clear, because it sometimes causes some confusion. So if I have these ratios or the amounts fed to the reaction, then what will happen is the 20 gram moles will react with only 10 gram moles. This is what I was just saying, that the ratio is 2 to 1, so the 20 gram moles of SO2 need only 10 gram moles. So I have 15. So what will happen is that 10 will react and 5 will be left over after the reaction is done. They are not reacting. They don't have any more SO2 to react with. And the product would be 20 gram moles of SO3 and 5 gram moles of oxygen. Okay, so given these results, we can see that the oxygen is in excess, meaning that it's more than the stoichiometric amount that we need. And if the reaction proceeds to completion, all SO2 would be consumed, and the some oxygen will be present in the product, which are the 5 gram moles. And this is a very important thing to know, because in most of the reactions that we perform, we don't stick to the stoichiometric ratios, and we add one of the or amounts of one of the reactants more than the stoichiometric ratios. And then comes the definition of the two terms, or the meaning of the two terms, the limiting and the excess reactant. So I think it's clear now what we mean by a limiting and the excess reactant. So the limiting reactant is the reactant that would be eliminated first if the reaction proceeds to completion, which is the sulfur dioxide in the previous case. This is what we call the limiting reactant, and we call it the limiting reactant because it is the reactant that limits the extent of reaction, or how far the reaction goes. So if the reaction stops and I add some more SO2, the reaction will start again. So it's what limits the reaction is the limiting reactant, which is the SO2. The other one is called the excess reactant, and which is oxygen, and which is more than the stoichiometric amount. Or the limiting reactant can be defined as the reactant that's present in less amount than stoichiometric proportions relative to the other reactant. So again, if we go back to this example, if all the oxygen will be consumed, then we need 30 gram moles. So this is less than the stoichiometric amount, or this is more than the stoichiometric amount, depending on which one you are taking as the basis. Is it the limiting or the excess? If we have both reactants are fed to the reaction with the stoichiometric ratios, then there is no limiting reactant. They're both consumed the same way. So this is the way we define the excess and the limiting reaction or reactant, or how we define them. Sometimes it's important. It's not sometimes. It's many cases where it's important to know which of the reactants is limiting. So we have a reaction and we have quantities of the reactants, and we need to know which of them is limiting. And to know which one is limiting, we need to look at this example for instance. We have propane combustion, which is the reaction of propane with oxygen producing carbon dioxide and water vapor. And the combustion of propane, this equation is balanced because we have 3 carbons, we have 8 hydrogen, we have 10 oxygen, we have here 6 and 4, so it's a balanced equation. So it says that 1 mole of propane reacts with 5 moles of oxygen. So let's say we feed to the reaction 17 gram moles of propane and 90 gram moles of oxygen, and we need to know which one of them is the limiting reactant. So you might think that the oxygen is much more than the propane as a quantity. So we have 90 gram moles of oxygen and 17 gram moles of propane, so definitely oxygen is the excess. This is not necessarily true. The way we can tell is by doing a very simple calculation, which is dividing each one of these quantities by its stoichiometric ratio or coefficient, the absolute value of the stoichiometric coefficient. Because we said before, the coefficient of the reactant is negative, so it's -5, and this is -1. So if we divide 17 by 1 and 90 by 5, we will get 18 here and 17 here. The value that is smaller corresponds to the limiting reactant. So the propane is, or the value of this calculation is less than the value of this calculation, then propane is the limiting reactant. And you might think, okay, so this is what we were saying from the beginning, that it's more than it's limiting. But let's consider another case where this number is 80, not 90. So if it's 80, this number is 16, and now the oxygen is going to be the limiting, although 80 is much more than the 17. So it's not necessarily that the species with the more number of moles, or the reactant with more number of moles, is the excess. It depends on the stoichiometric ratios as well. So this is one thing that we use a lot to find out which one is excess and which is limiting. There is one other thing that we, or term that we use to define how much excess we are using, which is not something related to the quantities as much as it's just ratios, which is what we like to use. So let's say for this reaction with the same quantities that we said, we have 20 gram moles and 15 gram moles, and we said that the 20 will be totally consumed and they require only 10 gram moles, producing 20 gram moles of SO3, and the product would be no SO2, 5 moles of oxygen, and 20 gram moles of SO3. So there is what we call the fractional excess. So this is it's not a quantity, it's just a ratio. And we like to use ratios because they don't depend on quantities, and you can apply this ratio to small quantities, to large quantities, and it's very, very common to use this term of the fractional excess or percentage excess, as we'll see at the end of this slide. So the fractional excess is defined as the excess amount divided by the theoretical amount. The excess amount, which is the number of excess reactant in the feed, which is the 15, minus the stoichiometric amounts, which are you can call the theoretical amount, which is the 10 gram moles. And you divide them by the theoretical amount, which is the 5 gram moles. So the 5 is the amount excess, so it's the excess number of moles of oxygen divided by the stoichiometric amount of oxygen. And in this case, if you calculate this, it's going to be 5 divided by 10, which is 0.5. Which is more common is to multiply this by percent, by 100 to be a percentage. It's like the percent, the mole fraction and mole percent. It's the same thing. It's the fractional excess. If you multiply it by 100%, it's going to be the percentage excess. This is very, very, very commonly used term in chemical reactions, and we're going to be using it a lot in this part of the chapter, inshallah. So I'll stop here and we'll continue next time, inshallah. So I'll see you then.